let's understand how the kinetic energy of a particle of a body which is executing SHM changes with displacements, or how the potential is changing, and what is the total mechanical energy of this system where there is no damping, there is no friction, etc. So that this SHM, once this body is put into SHM, this continues this motion for infinite time. We know the velocity is omega r square minus y square, where y is the displacement from the mean position. So let's consider a mass over here. This is a frictionless surface, horizontal surface. This is attached to a spring with a spring constant K. It has been pulled from here so that now it is oscillating between these two extremes and executing SHM. Let's say at any time t, it is displacement from mean position. So this is the mean position. Its displacement from mean position is suppose y, right? So at this instant, what is the velocity of this? Its velocity is given by v is equal to omega r square minus y square, where r is what? Where r is the amplitude. That is, this much is the amplitude. So this is projection of uniform circular motion once again on a plane where the amplitude is equal to r only. So over here the kinetic energy comes out to be, obviously that is we know half mv square, but now velocity is changing as the y is changing. So kinetic energy at any instant is going to be half m. Instead of v, we can put it over here. So it is going to be omega square r square minus y square. The thing to be noted is that is all the time this system has the total energy which is in form of kinetic energy and potential energy. So what we observe over here, that is because there is no friction, etc. So the total mechanical energy of the system will be conserved. It is, that is, potential energy plus kinetic energy of this system will remain constant. If it remains constant and suppose it has moved from here, from the mean position to some distance y, then v is equal to omega r square minus y square. So this is velocity function. Also, this kinetic energy is also known as half mv square. So velocity over here is this much. So kinetic energy comes out to be, in place of v, we put omega r square minus y square. So this becomes a velocity function. That is how the velocity is changing with y. So when it has moved from here to here, obviously there is some stretch in this spring also. This is not the natural length. So there is some potential energy also, right? But when it is at the mean position, then certainly all the energy is associated with the kinetic energy of this, because then there is no stretch or compression. This spring has attained its natural length. Now there will not be any potential energy associated with the spring. So the whole energy, total mechanical energy, is associated as the kinetic energy of this body. If you are interested in finding the kinetic energy maximum, which is also stands for when the kinetic energy maximum, that is at the mean position, we know at the mean position y is equal to 0. So velocity is maximum. When the velocity is maximum, kinetic energy is maximum. So it comes out to be half m omega square r square, because over here the velocity is y is equal to 0. So omega into r, if you square it, half omega square r square, that is the total kinetic energy, and this is also equal to total mechanical energy, because when it is at the mean position there is no extension or compression in the spring. So the potential energy of this is equal to 0, of the system is equal to 0. So the whole mechanical energy is represented in the form of kinetic energy of this block. When it comes over here, the velocity reduces because this is getting compressed. So velocity reduces, kinetic energy reduces, and this loss of kinetic energy goes into this potential energy of this spring. So all the time transformation energy between this and this is taking place. This is when it is going from here to here, its velocity is reducing, kinetic energy is reducing, and its potential energy is increasing. When it reaches this extreme, then it comes to a stop, that is kinetic energy has become equal to 0, and this is maximum compressed. So all the kinetic energy has gone into its potential energy. Once again, when it starts moving from here to here to here to here, then its potential energy is reducing because it is moving more towards its natural length, and its velocity is increasing, that is kinetic energy is increasing. When it is going this way, once again it is getting stretched, so potential is increasing and its velocity is reducing gradually, that is kinetic energy reducing. When it comes over here at the extreme, once again its velocity is equal to 0, that is kinetic energy equal to 0, and the stretch in this is maximum, that is all the kinetic energy has been converted into the potential energy of this spring, whereas the total potential energy plus kinetic energy of this system will remain as constant. At the mean position, that kinetic energy is maximum, so that also represents total mechanical energy. So at any given moment, the total mechanical energy, we can say it is going to be half m omega square r square. This is the total mechanical energy. Now we have found the kinetic energy as a function of y, that is how with y kinetic energy is changing. We also know the total mechanical energy also. we are interested, that is what is the potential energy as a function of y, that is displacement from moving position, that is at this position, then what is the potential energy of the system, that is now we are talking about this. Any body which is executing SHM can be related to this block and spring system. So total mechanical energy is this, so it is kinetic energy as a function of y plus potential energy as a function of y, that is at any instant kinetic energy plus potential energy is going to be constant. So it is half m omega square r square is equal to kinetic energy as y, as a function of y is what, this much, half m omega square r square minus y square plus potential energy as a function of displacement y. So this comes out to be half m omega square r square is equal to half m omega square r square minus, if you open the bracket, half m omega square y square plus potential energy as a function of y. So potential energy as a function of y comes out to be this, and this will get cancelled, this minus comes over here, so this comes out to be half m omega square y square. So this comes out to be potential energy as a function of y, and this is kinetic energy as a function of y, and this is total mechanical energy. So like this we can find the total mechanical energy, we can find the kinetic energy, we can find the potential energy also as a function of y.